All right, mathletes, here we are looking at reflections and rotations. So a reflection, we're going to have a mirror line, also known as a reflection line. So we have our original object, and we will reflect it across the mirror line. Okay, and notice that the image that we get after our reflection, again, just like our translations, is called the image. Some interesting things to know about reflections. Okay, the image is as far behind the mirror line as the object is in the front of it. That means the distance is the same from your mirror line to your image and to your mirror line to your original point. So mirror line to the original point here for B, notice that that length is the same distance from your mirror line to your image of B, that distance is the same. And that's similar, and we can note that by all of our congruent markers on these line segments, where this black line here is our mirror line. Okay. Second thing, the line joining any image point to the corresponding point on the object is a right angle. So you can see here they're all labeled here with right angles. They're perpendicular to the mirror line. All lengths and angles are the same size in the image as they were in the object. Again, it's just like a translation. It's the same exact object. It's just flipped across the mirror line. So there, it's what we call an isometry. Lastly, points on the mirror line are invariant. So if you have a point that exists on the mirror line, okay, so if we called this point D and we reflect it over the mirror line, it would also be D primed. That invariant means it does not move. Okay. So we also know that the mirror line, because not only is it perpendicular, but the lines are the same on both sides, so it bisects it. So kind of joining these ideas together, that it's a right angle and that the segments are the same, that the mirror line bisects the line connecting them. All right, let's look at an example here. So reflect each figure in the given mirror line. So doing this for a problem set, I'm going to be looking for corner points and just worrying about those and then connecting the dots. So for a triangle, I'm going to worry about flipping and reflecting that point, that point, that point, and just knowing that I'm looking for the equal distance away from the mirror line. So this distance here is 1, so I'd put a point there. This distance here is 1, so I'd put a point there. This distance here is 3, so I'd put a point there. And a little magic, and we see that we have our image. Okay, same thing with this one, but with curved objects, again, I'm just going to be focused in on corner points. So I'm going to be here, here, and here probably, and then just kind of fake the rest. So this is 1 away, so I'm going to put 1 there, 1 away, I'm there, 1 away there. I know that the height is 1 here, so we're going to get something that looks like this, and then a line across. Okay. So we get that object. So we could have a mirror line that's oblique or diagonal here. So notice that this corner point here is on our mirror line. So that one's not going to move. This one's here. So it's going to be the same distance there. This one's here. So it's going to be the same distance there. This one's here. So one diagonal this way is going to be there. And then because they kind of form the same shape here, I can also generalize, okay, and just say, all right, there is this L type shape there, and I get my image of that reflection. All right, let's look at another example here. So reflect this figure in the y-axis, so we can reflect over axes. Okay, this is going to be important as you look into transformations of functions. So again, the y-axis is here, that's my mirror line. So this point here is 2 away, so 2 away on the other side's here. This point's 3 away, so we're over here. This point here is 2 away, so I'm going to be over here. This point's 1 away, so I'm going to be here, 1 away there, and again, this one's going to be 3 away, and I can just make sure it preserves the same size and shape, although it is reflected across the y-axis. Okay, so another example. Or here we're going to talk about lines of symmetry. So a line of symmetry is a reflection across half of its figure, and the reflection on the other half of the figure is the same. Okay, so we can see with a isosceles triangle here that we have a line of reflection, okay, that can be drawn down the center. Okay, meaning if this was a piece of paper and we folded it in half, it'd be the same thing on both sides. Okay, there can be multiple lines of reflection. Okay, so if we look at a square, we have 4 different lines of reflection. They can be folded 4 different ways, and it'd be the same on both sides of the line. So if we were given these figures, we could draw lines of symmetry. So this flower pot looking is going to have a line of symmetry, so we could fold it down there. Maybe it's a little off there. It should be right in the center, about there. Okay. So for this other object, okay, we're not going to have a line of symmetry. Okay, it's not going to exist here in B, because as we would fold it here, if we tried to fold it there, right, this image would be over there, and this image would be over here, and that's not the same. If I did it over here, again, this would be up there, and that's not the same over there. If I tried to do it diagonally, okay, I get not the same image. So that does not have a line of symmetry. C, we're going to see 2 lines of symmetry, one vertically and one horizontally. Okay. So the other thing we're going to talk about today is rotations. So rotation is a transformation in which every point on the figure is turned through a given angle about a fixed point. The fixed point is called the center of rotation, and is usually labeled with a giant O. Okay. To completely describe a rotation, we need 3 things. One, we need to know the center of rotation. We need to know the direction. So direction is usually given as clockwise or counterclockwise or anti-clockwise. So anti-clockwise is the same thing as counterclockwise. Okay, and then we need to know the angle of rotation. So again, we do still call that the object after it's been rotated a image, and noted with our prime symbols here. So we can see this object has been rotated about our point O. The angle of rotation is 90 degrees, and since it's going this way, it's the opposite way of the clock, so it's counterclockwise or anti-clockwise. So rotate each figure O through about O. Okay, so we have this L looking shape. So if I want to rotate this figure, okay, and I'm going counterclockwise, so I'm going to move this point, and I'm going to go clockwise. So it's still going to be the same distance away from O. So if I rotate this 180 degrees clockwise, I'm going to be over there. Okay, this point 180 degrees clockwise is going to be over here. This point, notice it's 2 away here, and then it's going to rotate, and it's going to rotate up over there. Okay, and this object is 3 away from our center, so as we rotate, it's going to be 3 away from our center here. I can see my object forming that L-type shape. Because it's an isometry, it preserves all the angles and the size. There is my rotation 180 degrees clockwise. Okay, so now 90 degrees anti-clockwise. Okay, I'm just going to again think about some key points and then see if I can complete this shape. So I'm thinking about those key points. So if I go anti-clockwise, I'm rotating this way around. So if I move this point just 90 degrees, I'm going to go up here. Okay, if I rotate this, okay, 90 degrees, notice how it's a diagonal 2 away. So this new point is going to be 2 away there. Okay, notice that here, okay, I'm 2 away. As I rotate 90 degrees, I'm going to be there. So actually, I think this point ends up being there. Okay. As I rotate this 90 degrees, it's 4 away. I'm 4 up here. Okay. And then I end up seeing my object, so kind of a rectangle with a slice cut out, and that's being rotated there. Okay. So then this triangle, okay, I'm going to rotate 90 degrees clockwise. So clockwise is rotating this way. So maybe this point will be the easiest to start out with. So I'm 3 away, rotating it 90 degrees. I'm going to be 3 away there. Okay. Remember, this point's going to stay the same as I rotate it, because just like our line of symmetry, any point on the point of rotation is going to be invariant. Okay. So then as I rotate this point, okay, it's going to be diagonal 3 away. So as I rotate it 90 degrees, it's here. So I can see my triangle there. Okay. So last example here, we're going to state the vertex coordinates of the triangle ABC. Okay. Rotate the triangle 90 degrees clockwise about the origin. Okay. So there's my origin. So the vertex coordinates, okay, notice A here is -2, and 1, 2, 3, 4, 4, so that's A. Okay, B is -1, 4, okay, and C is -2, 1. Okay. So all those, I'm going to kind of move off to the side. Okay, and we stated our origin. So state the say the vertex coordinates of the image. So let's go ahead and find our image, and we'll put it in red. Okay, and again, rotate clockwise. So clockwise is this way. So here, point C, if we rotate it clockwise, is going to be now, this will be C primed. So C primed ends up being the coordinates. Oh, I'm sorry, that wasn't quite. So C prime 90 degrees is going to be here. Okay. And then, so that's C prime. Notice that this is going to be 1, 2. Okay. Let's do B prime next. Okay, so B was here. Okay, so as I rotate it 90 degrees, okay, I'm going to have B being over here, where this is going to be 4, 1, and A prime is going to rotate and be over here. That's A primed, B primed. And we see that that's our rotation. And notice A primed is going to be 4, 2. So we should recognize kind of a pattern here, okay, that to do a rotation 90 degrees clockwise, our X and Y values, they flip-flopped, okay, so the X became the Y, and that our X values changed signs, so they all became positive there. Okay, so that's going to conclude our notes tonight. Please highlight any questions you might have and bring